I'm going to be talking about what I learned working with improving the continuous integration for RISC-V. The intent is that at least some of this, probably a good chunk of it, should be relevant to you, whatever target you're working on, if you have any interest in LLVM's buildbot infrastructure at all. And one point just to clarify is that although much of this could be relevant to like pre-merge testing that we heard about before, I've been focused on the buildbot-based post-commit CI. So I thought a bit about how best to kind of transfer the information I wanted to. I figured I'll have a go at, rather than a war story of a blow-by-blow, this is what I tried, I'll go through some of the challenges I encountered and what worked for me and worked for RISC-V. So I have 10 challenges, less than 10 minutes now. We'll see how we get on. Firstly, this one is a little bit specific to RISC-V. It's an architecture where there's now a pretty reasonable amount of hardware in terms of development boards and the like, but there isn't a decent server class system you can stick in a rack. You can build, do a bootstrap build of Clang and LLVM and have it run in a reasonable runtime. So this is a challenge, and naturally the solution here is to use emulation with qemu, running on a fast commodity x86 64 host. So that is, you're sacrificing something in terms of speed versus if you had that hardware available. But if we can't have speed, at least we can have flexibility. So the dominant cost for setting up this infrastructure in the first place is engineering time. Hardware is very cheap. I can rent a server from Hetzner for 100 euros a month that's completely, very high performance for doing this stuff. And I don't have to worry about the hardware at all. And running under qemu, it gives us more flexibility in terms of testing instruction set extensions or combinations of instruction set extensions that may not be available in hardware yet, or even options for the extensions that may not be present in real hardware, but helps us to find bugs. So we have our qemu-based setup. We set that up and running, but as I say, it's a little bit slow. Running under full system mode emulation, this is where you have, it's simulating a full RISC-V system, including running a Linux kernel compiled for RISC-V, doing a full two-stage bootstrap build, running the included unit tests. Takes something like 16 hours. What can we do about this? Cross-compilation obviously comes to mind, because then we can compile everything as fast as we possibly can on x86, but how do we run it? qemu user is another option. This is a separate kind of mode of using qemu, whereby rather than simulating a full system, it's performing translation at the syscall level. This is a little bit faster than qemu system, somewhat more scalable in that it can scale to. qemu system has reasonable scalability across multiple cores. qemu user can do a little bit better, at least in the kind of separate process build setup. But it has issues in terms of emulation fidelity. By that I mean, if you find a bug or an issue, what are the chances that it is an artifact of the setup that you have in order to actually do your testing versus a real problem? So the solution I've ended up at, which I think could actually be quite helpful for others, I've written about it a bit if you look at my blog, and also look at LLVM-Z, or all the scripts needed for it are in there. So we do a cross-compilation and then spin up a kind of appliance virtual machine that's running. So it's a RISC-V base system, attach the generated build artifacts as a kind of mounted file system, then switch to that to run the tests. We have a wrapper script around LLVM lit that makes this kind of transparent to the LLVM build system. And this works very well and doesn't have the same limitations that qemu user has in terms of lack of support for ptrace or issues around handling of sanitizers and that kind of thing. Compiling Clang and LLVM, running the unit tests, it's a challenging workload, but it doesn't represent everything that people do with the compiler. It represents most of what I do with the compiler, but not the wider world. And so there are more things you could do to widen the testing pool, but at least the minimum is going ahead and adding in the separate LLVM test suite repo, building that, running the tests. I actually run that with qemu user, as the kind of requirements there are fairly minimal. It works nicely. And on qemu user in general, I did upstream a few fixes around working with that with LLVM. So it works reasonably well for baseline unit tests if you wanted to go that route. And this one might be a bit surprising, unless you're a much better engineer than I am. Probably you know all the things that I've described. It's conceptually fairly reasonable, but you're unlikely to write out your build script and it works perfectly first time. And a long-standing issue we've had with the LLVM buildbot infrastructure is actually quite hard to go and test things downstream without committing it to LLVM-Z.org, waiting till it gets deployed on the staging build master, and seeing if it works or not. A few people had some kind of downstream patch sets around this. I went ahead and upstreamed support for a local testing mode, as well as writing up documentation. So it's now super easy to set up a new builder, test it locally, or modify an existing one and push it upstream. It's been a huge improvement for me in terms of my workflow. We also have some CI for our CI in that I've added a few simple GitHub actions to check that if you're modifying the kind of core LLVM-Z.org Python scripts, things still work with at least some simple tests. I've maybe been a bit verbose here, but the point here is really the LLVM-Z.org infrastructure. It has a bunch of kind of reusable recipes for building, like say a Clang CMake factory. You parameterize that by a few options. This is great if you want to do something that's just like an existing builder, but a little bit different. But you start to change one thing, you change another, you need to add some new parameters to that function, thread it through, it may interact with the ways other people are using it in unexpected ways. This is mainly an advert for the annotated builder infrastructure, which lets you commit a shell script that does the build steps you want to, very easy to iterate and change. And related to the next challenge, makes it a lot easier for people can literally just check out that shell script, and if you write it in a way that allows this, they can just run it without caring about the rest of the buildbot infrastructure. Another issue we had here was cross-compilation not being well documented. There's now a upstream documentation that gives a modern flow on how to do this in a way that works. A more recent change has been deploying a new builder type. This is what I call, so we've kind of said that, well, maybe I didn't say, but we went from 16 hours, the kind of cross-compile and then run on qemu system. That's about 1.5 to 2 hours. That's still multiple commits in a single batch typically. So can we do something better here? My observation was that when I find a regression flagged by the builders, I tend to go through a fairly similar set of debugging steps, and why don't I set up a builder that does this? So doing a cross-compile of Clang, doing a compile of fresh Clang and LLVM, and then compiling and running multiple configurations of the LLVM test suite, limiting the test to just those that can run in a relatively fast time, gives about 5 different RISC-V configurations, a runtime about 25 to 30 minutes. I kind of set this up as what I call the gauntlet builder. The idea here is that it's adding some extra testing alongside what you already have. We already have the separate builders which are providing tests that are a bit more detailed, they're running longer. But if you had a failure on one of those slower builders, but you didn't see it on the faster one, that's useful information to debugging. If you have it on both, you've got a head start on actually working out what the issue is. And as I'm kind of hinting at here, clearly, there isn't a one-size-fits-all approach. I've talked about going from like a 16-hour time to 1.5-hour time to 25 minutes. These are all testing different things with different trade-offs in terms of what you cover, what the fidelity is. Having a combination of these, I find, works really well. The final thing here is that the buildbot interface is quite powerful, but not that great for flicking through, particularly if you're only interested in a few builders. So there's a nice dashboard set up to look at, in my case, I'm mainly interested in the RISC-V ones to see where they're at, what their runtime's like. So I wanted to thank everybody who has helped working on this, particularly reviewers and those who are maintaining the buildbot infrastructure. A fairly thankless task, but we're grateful to everybody who's been incredibly responsive with reviews or questions. And thank you to RISE for supporting this work. If you have any questions or you're looking to try and apply anything I've talked about, just talk to me afterwards or drop me an email. Thank you very much.